Okay, which choice most effectively uses data from the graph to complete the assertion? We've got a command of evidence quantitative. We've got to complete the assertion. Let's take a quick peek at the graph. We've got number of infrared beam breaks by mice treated with CNO or saline by sex. So the number of beams vertically, the minutes from treatment horizontally, and we can see what happens here. Females with CNO, whatever that is, it jumps up a lot within 30 minutes or so. The others kind of not too much movement, but they all seem to trend downward after that 30 minutes. Okay, let's see what's going on from the text. To investigate the influence of certain estrogen-responsive neurons on energy expenditure, biologists such and such treated female and male mice with either saline solution or clozapine, N4 oxide, which activates the neurons. So I guess the saline solution is the control. It's basically the nothing, would be my guess here. And then the clozapine would be the actual estrogen neurons that are being affected here. So monitoring the activity levels of the mice by measuring how frequently the animals broke infrared beams crossing their enclosures. So they're running back and forth. That's the idea, going back and forth. That means high energy. Found the mice in their study showed sex-specific differences in response to neuron activation. Okay, so what do we see? We see the females within 30 minutes, they show a huge jump with this extra clozapine or CNO, whatever we call it. So A, the 4 groups of mice differ greatly in their activity levels before treatment, but showed identical activity levels at the end of the monitoring period. So they were the same right before the treatment. So they're not different. That's wrong to the graph. And they came close to the same, but not exactly the same by the end. So this says the 4 groups differed greatly. That's wrong. So inaccurate to the graph. B, saline-treated females showed substantially more activity at certain points in the monitoring period than saline-treated males. Not the saline-treated, the CNO. That's not right. CNO-treated females showed more activity relative to saline-treated females than CNO-treated males showed relative to saline. Yeah, the CNO females jumped dramatically. So that is true. That's accurate to the graph. And that shows sex-specific differences in response to the neurons. So it's relevant to our claim, and it's accurate to the graph, which is what we need to find for all these quantitative questions. Let's just check D. CNO-treated females showed a substantial increase and then decline in activity of the monitoring period. That's accurate. Whereas CNO-treated males showed a substantial decline in activity, followed by a steep decrease. So this does show some sex-specific differences. I'm not sure this is accurate. Was the male's substantial decline after treatment? No, males actually went up a little bit. So this is just, this last part is inaccurate. It's not true according to the graph. C is the answer. Okay, we need data from the table to illustrate the claim, which is here at the end. Okay, so let's take a quick look at our table. Ebook sales is a percentage of unit sales in all book formats for a large U.S. trade publisher in various different years. So different years, we've got different genres. Ebook sales have jumped in every single genre, from near zero to substantial. So yeah, ebook sales, okay, in just 10 years. So that's clear. Ebook sales became an increasingly popular means of reading in the United States in the 2000s and 2010s. Okay, that's clearly justified by the table. That popularity was concentrated in titles that, like those in most fiction genres, are meant to be read straight through from beginning to end. So the popular ebooks you read in one sitting. For books in nonfiction genres that do not tell stories and require the reader to flip back and forth through a volume, ebooks were significantly less commercially successful. So if you flip back and forth, not as commercially successful. And we kind of do see that. So what would I flip back and forth between? A cookbook to check my recipes. That didn't go up quite as high as the others. Maybe even a travel guide. I might go back and forth referencing it. So this can be seen by comparing. My predicted answer here would be comparing the high jump in romance and science fiction versus cookbooks and travel guides. Let's see. The percentage of 2016 cookbook sales that were ebooks with the percentage of 2016 science fiction and fantasy sales that were ebooks. By comparing 2016, yeah, that's probably the year I compare them because they're all 10 years earlier or near so. Just cookbooks, not travel guides. I mean, this is the main one. So I'm going to check that. That looks good. Let's just check other answers. The percentage of 06 romance. No, I wouldn't check 06 to 16 and not just on romance. That doesn't tell me anything about the claim that flipping back and forth is less commercially successful. C, the percentage of 2006 romantic sales that were ebooks of 2006 science. No, 2006, they were all low. That doesn't tell us anything. The percentage of 11 that were ebooks. No, that doesn't really tell us. The best answer is A. It started at 0 in 06, all of them. So I just checked the cookbook sales, the most flip back and forth one, versus the science fiction and fantasy, where I'd sit down and read it all at once. Those were much higher. Okay, which choice best describes data from the table that support Rodriguez and colleagues' assertions? So let's figure out what their assertion is, and we want data to support that. So I've got different exoplanets, and I've got a mass and a radius, an orbital period, and a distance from the sun. So, okay, so I've got various factors or attributes of the exoplanet and different exoplanets. And what do I notice? If the mass is higher, radius is not fundamentally different. The orbital period is shorter, so higher mass, shorter orbital period, and closer distances with one exception. Yeah, that one there. Okay, so something's going on here. Let's see what the claims are. Hot Jupiters are gas planets that have a mass of at least 0.25 Jupiters, meaning their mass is at least 25% that of Jupiter, and an orbital period of less than 10 days. Okay? Meaning that they complete one orbit around their star in less than 10 days. Wow. Okay. That's why these numbers are so low. That's not a hot Jupiter, technically. While warm Jupiters are gas planets that meet the same mass criteria but have orbital periods more than 10 days. Okay, this would be a warm Jupiter right there. In 2021, Michigan State University astronomer Rodriguez and colleagues announced the discovery of 5 new gas exoplanets and asserted that 4 are hot Jupiters, 1 is warm Jupiter. That's true, right? The data here in orbital period supports that. 4 are less than 10 and 1 is just over 10. That's the claim. All right, well, let's look at the evidence. It's pretty clear. None of the planets have an orbital period of more than 10 days, and TOI has a mass of, okay, so that's not true. There is one that's more than 10 days. TOI has an orbit, we don't care about the orbital period of 153 days. No, that's not what it is. That's distance from the sun. That's mixing up the facts. So that's not right. All the planets have a radius. We don't care about the radius. Each of the planets has a mass greater than a quarter Jupiter's. Yes, we need that to be the case. And all except for TOI have an orbital period less than 10 days. That's true. This is the best evidence to show that. Okay? And just a warm, it just says more. It doesn't have to be close to 10 days or not close to 10 days, just more. So D is correct. It's accurate to the text and answers the question. Okay, which describes the data in the graph that support the student's claim? Okay, so we'll read the student's claim. Let's just take a peek at the graph, see if it tells a story, and if we understand it. So that's really important. If you understand the graph, you're probably in good shape for the question. If you don't, usually that begins to, errors creep in. So rotor diameters of newly installed wind turbines in the United States. Okay, so if I have a wind turbine, let's say, and it's flipping back and forth, this is the diameter. So D, okay? Percent of newly installed turbines, okay? So what do we have? We have that versus the year. So newly installed turbines, we've got, okay, what all these graphs are, they're different diameters. Okay, I kind of see what's going on. So what's the story? Less than 100 meters was the case over 10 years ago, and that dropped dramatically. What's replaced it is longer, 100 to 130 meters going up. And, as the bigger one came down, the new, even bigger one came out. So we keep replacing with bigger diameter turbines. Okay. So all other things being equal, the larger wind turbine's rotor diameter, the diameter of the imaginary circle swept by the turbine's rotating blades, the greater amount of energy the turbine can generate. So bigger diameter equals more energy, which is why we keep replacing with bigger turbines as bigger rotors. In a research paper on wind power, a student claims that the United States, the amount of energy generated per newly installed turbine increased substantially between 2000 and 2021. We need to support that claim. Well, what supports it? We had higher diameters, and higher diameters are associated with more energy. Let's find that answer. The percentage of newly installed turbines with rotor diameters greater than 130 increased every year between, it probably did, but I don't think that's really the answer. No, it was 0 or flat for the first few years, okay? In 2011, so that's not really going to answer our question. In 2011, nearly 80% of turbines installed had rotor diameters less than 100 meters, whereas only a little more than 20% of turbines installed in that year had rotor. Okay, that doesn't tell us change. That's a snapshot in a year. We don't want a snapshot. We want change, how we keep increasing with greater diameters to produce greater energy, and that would support the student's claim. No turbine installed in 2011 had rotor diameters greater than 115, whereas the majority of turbines installed in 2021 had rotor diameters greater than 130 meters. This looks pretty good, right? It shows a growth in diameter over time. Maybe there could be a better answer. Let's check D. Most turbines installed in 2011 had rotor diameters of less than 100 meters, whereas most turbines installed in 2021 had rotor diameters of at least 115 meters. So that could be good too. Is that true to the text? So most, basically this is percent, so most were less than 100 meters. That's true, accurate to the text. Most in 2021 were at least 115. So 115 is only the starred package, and that's over 50%. So that's true as well. Okay, so this is accurate, and that does support our claim as well. So D looks pretty good as well. Let's go back and check C again, see which one's better. C says no turbines in 2011 had rotor diameters greater than 115 meters. Greater than 115, yeah, it was 0. So that's true, that's accurate. And whereas the majority of turbines installed in 2021 had rotor diameters no, that's not accurate. Greater than 130 meters, there's no greater than 130 meters. Okay, so just a slight inaccuracy in the graph. So D must be our answer. It's supporting the claim, bigger diameter, bigger energy, and it's accurate to the graph. D is the answer.